Good evening, everyone. Today we talk feature engineering. Thanks for the reply. Many people gave a feedback. I hope you will reply to this as well. I mean, more technically, let's say. But yeah, as I wrote, we're gonna present in Abu Dhabi the work we've been doing on feature engineering mainly, but not only. We're gonna talk in general about CrunchDAO to people working at the Abu Dhabi Investment Authority Fund. And yeah, it's mainly about feature engineering and the work we did in the context of the master dataset release. But there's some portfolio optimization and portfolio management together with machine learning in the presentation. So I'm gonna share the notebooks soon. Today I want to finish a couple of things that I'll say later. So I'm just sharing the screen and showing you the pipeline. Please give me your feedback. I mean, take a look. Then maybe I hope tomorrow I'll be able to share the notebooks finished. And because yeah, tomorrow we have to do the slides for Abu Dhabi. So please come back, take a look as soon as you can. Yes, so let's start. Empty notebook, empty kernel, we start. We import factors. Maybe you don't know it, but we are building a zero beta product, which means that we have to be orthogonal in a linear sense to a set of factors which come from macroeconomy. So they are linear models that express in a sparse sense the behavior of the overall market. So there are like models with only two factors, 1, 10, 100, 1000 even, which is a small number in the majority of these cases compared to the number of stocks. So we want to be orthogonal, therefore we need them to inform the features, the dataset, with this information. And at the same time we have our features. So now I'm using a subset of features. Just to give you an example, we have 5 features. And actually I'm also giving you a subset of epochs so we can train easily. 2 years. And yeah, this is the feature we're starting with. How we end up with this feature, a lot of work. I mean, you know where C mechanics, Dolly, what they mean. Here we're putting everything together, so the physical meaning, give me the chance to use this term, is different. They are correlated, these features. Now I'm looking at Spearman correlation, but the Pearson is quite similar. And so we'll try to do something about this as well. But most importantly, they are correlated with factors, underlying macros of the market, and we don't want that. So given that you are building models on these features, and given that we want your output to be orthogonal to these factors, to help you do that, we orthogonalize features themselves. So how we do it? Okay, first of all, let's take a look at the statistics of these features. Some are pretty Gaussian, some are not even unimodal, and in general they're highly skewed slash they're characterized by a high kurtosis. So that will be an interesting step. So what we do, we start looking at the factor exposure. Here I'm computing just the norm of the exposure of to all factors. So it's like a root sum square exposure. And you see it's non-zero, and it's also changing in time. We want to do something about it, so we run this orthogonalization step. Here we are, for each epoch, so for each tournament round, we're taking the features of that week and we're making them orthogonal in a linear sense to factors. Now you have to know that factors are not orthogonal to each other, so we cannot orthogonalize to all of them. We can orthogonalize in a linear square sense, in a least square sense. So we use a least square, so we do matrix multiplication basically, and we project the feature into the space of factors, again expressed in a least square sense, and we subtract that component from the original feature. And so after doing this, we get a root sum square exposure, which is 0. Now, you need a spoiler to understand the next section. So here, actually, this is the thing I'd like to compare with the coming correlation covariance matrix. Because here, all these features are now in a space which is orthogonal to factors, which is where we want to be. So now we'll try to also make this thing as diagonal as possible. Yeah, and these are the features after orthogonalization. They behave much better, which is good news. And yeah, I'm saving, I'm also gonna share the files. So yeah. Then here I wanted to show something which is related to alternative ways of dealing with high kurtosis in features, or in general in datasets. One simple way is to Windsorize data after 3 standard deviation and then treat the Windsorize features as a Gaussian, to be characterized by a Gaussian distribution. You see that basically the Spearman of the Windsorize feature with itself, with the original one, is high, and but the Pearson degrades quite some, particularly for some epochs. Yeah, you see here 75%. Other features which are already pretty Gaussian maintain a high Pearson with themselves. So now the idea is, I think I shared the link on this, but my way of thinking about it is that we learn from the average 4 statistical moments of each feature. For each feature, and this is also an assumption, we learn a kernel, so we impose a nonlinear metric on the space defined by the feature, such that the image of this feature on the space is Gaussian. We are doing it in an univariate sense now. One could think of defining a single metric for all the features that make the multimodal distribution of all the features a multimodal Gaussian. We didn't try that yet, but I think there could be value in doing that. Yes. But yeah, let's focus on one by one for now. So we are defining a different metric for each feature, which makes things easier and gives us hope, which in fact is not so ill-posed. I hope that's the right word in English. So yeah, this is the distribution at the beginning of the processing of this step. This is the time series of the mean, standard deviation, skewness, and kurtosis of these features. You see that they're not stationary, and that's a problem we'll have to deal with. But yeah, you see that after Gaussianization, we break something, but not so much. There are some Windsorization steps that destroy more than what Gaussianization does, and you see that then when we come out, the feature is pretty Gaussian. These more skewed ones, sorry, I don't know the adjective of kurtosis, but you see here there are some peaks on the kurtosis, so we are not as able, sorry, we are not, come on, sorry. Okay, I lost it. Yeah, we're not as able to Gaussianize things. This was already Gaussian, so we're good. This one was, again, highly volatile in kurtosis, so it's not as easy to Gaussianize them. But still, the good thing is that here the kernel is unique across all the epochs. We learn one kernel that's Gaussianizing the feature across all epochs. So the transformation is stationary. Okay, now we can recompute the exposure, because being the kernel nonlinear, I'm thinking it in linear algebra sense. So there's a vector and a plane spanned by the factors. And yeah, first we orthogonalize it, and then when we apply this Gaussianization step, we are re-adding again some factor-related a factor-related component, which we can remove again without destroying Gaussianization. That's good news, because basically we can get out of this part with a zero exposure to factors, so correlation, but also maintain the Gaussianity. So you see these are the distributions, kinda Gaussianity, but overall we are kind of happy. So yeah, how do we move forward? Yeah, here I wanted to show the correlation between the sorry, here I forgot to remove the debugging thing. So I'll skip it, but I wanted to show the correlation between the doing Gaussianization and orthogonalization against doing only orthogonalization. We lose a bit more than Windsorization, but I have to say that after Windsorization, I didn't orthogonalize again. So it could easily be that Windsorization plus orthogonalization destroys more than Gaussianization and orthogonalization. Yes. But why are we doing all this? Why do we want a Gaussian? Because, well, if we can come out of this with a Gaussian orthogonal feature, then, and these are the features after, I think I standardize, yes. So that the upcoming step will not take care of the fact that different features having different physical meaning are associated with different standard deviation values. You cannot compare 3 kilograms with 2 seconds, you know. So you cannot compare different features with different standard deviations, so you normalize. And yeah, we are here, zero mean, zero standard deviation of features, and we can compute the time series of the lower triangular part of the covariance matrix of these features. And it's not stationary, which would also make the possibility of finding a single kernel that makes all features, that brings all the features to a multimodal Gaussian quite impossible. But probably that could help. Because then we do principal component analysis in this space in which things are Gaussian. And things make sense because PCA minimizes the unexplained variance. And actually what we're doing here is using the same number of components in the PCA as the number of features as an input. So basically we're just doing a basis transformation, linear, such that the basis is as orthogonal as possible. So these features are basically, I don't know, alpha feature 1 plus beta feature 2 plus gamma feature 3, etc. And they're as orthogonal as possible in a linear sense. Then we can standardize again, and because it was not granted that a linear combination of standardized Gaussians is still standardized. But we can do all of this because these are all linear transformations. So after we did the last orthogonalization, we just did multiplication, I mean division, but it's a multiplication by a constant. Then we did PCA, which is a linear combination of features, and then again we are standardizing, so we're still in a space orthogonal to factors, so we are happy. Unfortunately, being features non-stationary, we have some degree of correlation between them. It's much smaller than what we had before, but still, for example, I mean, we cannot say much as I'm doing this analysis on 5 features, but still, here we have these 2 features a bit correlated with each other. But okay, overall it's pretty dark, so it's good. Same with Spearman, and we can go forward. Now we have these beautiful features that we cannot share, unfortunately. But we can do quantization. So we can think of these as Gaussian processes. This should not be thought in time. Here I think I'm plotting, yeah, just epoch 0. So yeah, these are all the stocks. It's the universe for that epoch, for that feature. And the evaluation of the feature is distributed like a Gaussian. So the natural choice of quantization is this Lloyd max quantizer, which is kind of like a k-mean clustering technique for Gaussian processes. And it's optimizing for the location of the centroids such that they explain variance once again. And that's why we wanted to go to Gaussians, because we are always working with explain variance correlation, in which either we have a L2 norm error or we have a correlation distance. So a Gaussian space is the most natural choice. So yeah, we can use again a clustering technique for quantization that optimizes for the explained variance because we are in a Gaussian space. We can do this. Also, we can do this, maintaining the. We are agnostic to the number of bins we want to quantize to, and it's not impossible to think that given all the transformations we are now doing, we will be able to. We will need to anonymize. We already have anonymized quite some data, so we can think of. And I'll show you on the target, so it takes less. But yeah, these are the features you will recognize. But these are all the steps that led us to these features. Now, yeah, after quantization, basically the covariance matrix doesn't change, which is good news. But yeah, what I wanted to say is that we can define the number of bins we're interested in. Here, I call it bits. But yeah, let's look on the target because I think things get much more interesting on the target. Of course, target. Now I'm working with just one target, and probably we will not. Even if we work with multiple, we don't need to do. I mean, we don't want to uncorrelate targets because targets bring their own meaning to the game. So the distribution of targets. I'm now on target W, but I would expect all the targets to be like this. Is again fat-tailed. Sorry, and so we are thinking about something about this. We do this Gaussianization, and here I think you have the 4 statistical moments of the target. Yes, and here we have the again Spearman with the original target and Pearson with the original target after Gaussianization, and this is the Gaussianized target. The good news here is, and I'll show you, that the kernel, and again, hi Hilbert, yes. If we come back from the kernel from the Gaussianized space using the inverse transformation that we used to Gaussianize, so we have an inverse, we are back with 100% of the information. And this is great news because we can think about using this target, this Gaussianized target, as a target in the tournament, so that all the optimization steps make sense because everything is Gaussian, both the features and the target. But then, yeah, probably, I don't remember. Yeah, here I'm standardizing because the quantization step requires variance 1. Otherwise, it's unstable. But yeah, here I'm quantizing the target, and I can show you the target. It's a Gaussian, but with bins. So if I go up, and we want 11 instead of 5, we can have 11. And sorry, it's not here. Where are we? Standardize, target. Did I overwrite the target? Yes, I did. So let me rerun briefly all the steps. Sorry. Yes, let's go from here. Actually a target row. Okay, I'm lazy. Let's do it again like this. And you'll see that the bins are again fitting a Gaussian, but we have more bins this time. You see? And of course, the more the bins, the more the information in the dataset for the tournament. And given that this is a kernelized version of the target, we should be able to afford it. We look into this in the coming weeks. Then, spoiler for the things that happen outside the tournament, but I think it's interesting also to think about the scoring mechanism. We can, I don't know, here I'm building the submission, adding Gaussian noise to the target of that week. So this is what someone is pushing. Good. Okay, one could say why Gaussian noise and not non-Gaussian? Everything is Gaussian, so maybe it's not a big assumption here. But then what I'm interested in doing is someone is pushing this in Gaussian space, so in the target. And we know that the target is optimizing for Spearman. And since we know that in this Gaussianized space, the distribution of targets is Gaussian, we can say that the optimal weights for the portfolio are the dekernalized. So we apply the inverse transformation that gave us the Gaussian distribution. We apply it to an alpha score, which is basically the cumulative Gaussian. And we get this, which is good news in the sense that we can, you see, this is the theoretic distribution of targets given this target and this kernel, because this is the inverse transformation of a Gaussian, which is kinda matching. I mean, it's exactly matching this kind of transformation. Now you don't see it because here we have big outliers, which we don't have in this theoretic case. Sorry. But yeah, this is telling us something important, which we'll need to discuss, I think. If things were Gaussian, the tails would have been more important than the center. But things are far worse. So picking the right stocks here is really, really important. Much more important than having working in a Gaussian framework, even with the targets we are using now. So we'll need to think about this carefully. But it's good news because we have this one-on-one correspondence between the Gaussianized target and the non-Gaussianized. So we can keep working on Spearman, and we can come back to the physical space, let's say. So this is all we're going to present. I think there's going to be something else about I don't remember what else. Yeah, I mean, the last thing I said is kind of related to how to measure risk. But yeah, that's all. What do you think? Please come back with a feedback. I'll share the notebooks. Let me finish something which I didn't share now. But the problem is that now I'm doing quantization, looking for the optimal bins on a weekly basis, which leads to a non-stationary transformation. So I should do it differently. But once that it's done, it will be out. I think that's it. Yeah, then yeah, some minor modifications. So what do you think? Let me know, let us know. Help us build a super cool paper and presentation to destroy everything. I don't know how to say in English. I'm thinking in Italian. I'm tired. See you.